Okay, so before we studied an asymmetric encryption technique, the RSA. Now we're going to study the symmetric encryption standard, which is known as Simple Data Encryption Standard, SDES. Now, as we are familiar with symmetric encryption, that means that both encryption and decryption on both computers that are sending and receiving data is done using the same key. So basically what this standard does is that introduces the encryption mechanism in which we're using the same keys. Okay, now for SDES, many years data encryption standards was the normal choice for symmetric key encryption. As the weakness of DES becomes, triple DES took its place. In 2001, Advanced Encryption Standards AES was introduced as a superior approach. For education purpose, only a simplified DES or SDES was introduced, which allowed the sort of operations performed in encryption to be better understood. Now, SDES is what is known as a block cipher. By block cipher, it means that it takes 8-bit data blocks and encrypts those block by block. So basically what we see here, this process, this complete process of encryption is being performed on each block of data, of plain text, right? This is known as a block cipher. It doesn't take all data and combines that and encrypts it in one go. It takes it block by block, right? So we will look at the steps involved in SDES, and for SDES, we will be using these different key values, okay? These considerations will be used. So first of all, the plain text that I'm using will be this string. This is my plain text string, 0010100000, okay? So this is my plain text, and when I'm done with encryption, this plain text will be converted into my ciphertext using this technique. This is a 10-bit key that we'll be using. Right now, this is not the original key that I'm using. You can say that it's a randomly generated key. And the first step involves by creating 2 keys from this one plain key, 10-bit key. Okay, this is known as the permutation 10. You will be hearing this term permutation a lot throughout this whole technique. We got permutation 10, permutation 8, initial permutation, inverse permutation, permutation 4, expansion permutation. We'll be seeing these terms a lot. Basically, what permutation means is the order of bits. So basically, permutation 10 means original data, whatever it was, 3rd bit of the original data will come first. Then 5th bit of the original data, then the 2nd bit, then the 7th bit, then the 4th bit, then the 10th bit, then the 1st, 9th, 8th, and 6th. So basically, it's a technique for rearranging the bits. Same thing is happening with permutation 8. I'm taking the original data, whatever it is, and reorganizing it using this sequence. And as with any permutation, this is known as the expansion permutation, and this is only applied to a nibble, just one nibble, one what you call it, only 4 bits. So bit number 4 comes here, then 1, then 2, then 3. Then another following 4 more bits, 2, 3, 4, and 1, like so. Okay, this is known as expansion permutation. Now, these expansion permutation, in fact, these permutations that you see here, these are predefined and they're fixed. So this sequence of numbers you get here, they'll always be the same way, exact same way, okay? So you'll be needing these permutations in this sequence at some point. So we'll be looking at how they're being used later on. Apart from that, we'll be using 2 SBox values. This is known as SBox 0. This is SBox 1. So how SBoxes are used, you'll be looking at that too. So basically, we'll be using all of these different values and techniques to apply SDES technique, okay? So let's start with the first step, step number 1. Step number one is known as the key generation technique. Now, basically, the outcome of this part of SDES is that I will have two keys. Okay. Now, how do I get these two keys? Okay. Sub-step of step number one, the first phase of step number one is to take that 10-bit key, namely this key that we're talking about right here, and apply P10. Remember what P10 was? Permutation 10. Permutation 10 to get a temporary sequence, which we will call A. Now this A, it could be anything. We just named it A for our sake, for understanding, okay? So first step is that we'll get A. So let's see that these are my bit positions: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And this is the 10-bit key that we were talking about: 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. So as mentioned before, this is my 10-bit key that we'll be using here. You see, exact same key that we discussed is written here. So bit position 1, 2, 3, starting from the left, increasing towards the right. This is my bit position, and this is my original key. So permutation 10 requires me to rearrange these bits according to this sequence. So first, bit number 3 of the original 10-bit key should come. So as you can see here, bit number 3 of my original 10-bit key is 0. I get 0 over here. Then I need bit number 5. That's 0 over here. Then I need bit number 2, which is 1. Got the 1 over here. Then I need a 7, which is another 1. I got that over here. Then I need a bit, the 4th bit, which is 0. Then 10th bit, which is another 0. Then the 1st bit, which is a 1. Then the 9th bit, which is another 1. And then we got the 8th bit, which is another 1. And the 6th bit, which is also 1. So when I apply permutation 10 to my original 10-bit key, this is my resultant, which we are calling A. So A is P10 on my 10-bit key, and this is the result. Understood?
Understood.
Okay. Second step, we will perform a logical shift by 1 bit on LS1. So 1 bit. So LS1 means logical shift 1. So logical shift by 1 bit separately on each half of A to get B. So what means is that we will apply LS1 on the first 5 bits, then LS1 on the remaining 5 bits, and we'll end up with B. So as you can see here, this is my A, and logical shift by 1 bit means that I simply take all of these bits till here, and I'll move these 4 bits 1 position to the left. And by the way, any bits that I'm dropping from this side will end up on the other side. So basically, if I'm losing this 0 on the left, it will end up at the tail. So 0, 1, 1, 0 will come.
So you only do the first 5 bits?
Only half of it, only half at a time. We don't do it completely.
Why half at a time?
Okay, half a time. Okay, so on the first 5 bits, I will take the entire sequence and shift it 1 place to the left. So basically, what happens is that these 4 bits will become the most significant bits. So 0, 1, 1, 0. Agreed? And this 0 that we lose on the left side ends up at the tail. So the resultant sequence is 0, 1, 1, 0, and this 0 ends up here. Okay? Is that okay?
So why do you only do half?
That's the rule. That's just the way it is. Okay?
So the last 5 bits don't get touched?
No. The last 5 bits are handled separately. LS1 is applied separately to them.
When? Oh,
right now. See, now these are the remaining 5 bits. Now I'll apply LS1 to them separately. So what happens is that these 4 ones will move 1 space to the left, and this 0 will end up at the tail. So I'll be left with 1, 1, 1, 0.
Okay.
And when I combine these 2 halves together, I get B, which is 0, 1, 1, 0, 0, 1, 1, 1,
What
0.
do you mean by combine these two halves together?
I just write them together, form 10 bits together.
I don't know why they shift up the logical shift like that. Why do they do half then, half there?
That's just the sequence. That's just the algorithm.
Right.
Okay. Okay. Now, next step. We got B. How did we get B? We applied LS1 on the first half and LS1 on the second half, and we wrote the 10 bits again together, and we got B. Okay. Now, since we have B, the next step is that we perform permutation 8 on B. So basically what permutation 8 does, it arranges the sequence of 10 bits only to 8. So you start with 10 bits and you're left with only 8 bits. But which 8 bits and when what order? This is the order that's mentioned in permutation 8. So first, from permutation 8 that is performed on B, this is B right here, I need the 6th bit of B to come first. So I have 1, this is my 6th bit. Then I need 3. 3 is 1 again. Then I need 7. 7 is 1 again. Then I need 4. 4 is 0. Then I need 8. This is 1. Then I need 5, 0. Then I need 10, 0. And finally, I need 9, which is 1. And this is my resultant after performing permutation 8 on B. And this sequence of 8 bits that I just got, this will be my key 1. So as mentioned before, in the key generation phase, we're going to start off with the initial 10-bit key, and we're going to be ending up with 2 8-bit keys. So this is that first of those 2 keys. This is that first 8-bit key, okay? Now, how do I find the second 8-bit key? So now we take B, this was my original B, this right here. And this time we do LS2. Now what is LS2? We perform a logical shift of 2 bits on each half. So instead of, doing 1 logical shift, we're performing 2 shifts, okay? So this is my original B right here. So what that means is that these 3 bits, they will end up at the start, 1, 0, 0, and any bits that are moving from here will end up at the tail. So basically what's going to happen is that 1, 0, 0, followed by this 0, followed by this 1. Agreed?
Correct.
So we got 1, 0, 0, 0, followed by 1. So this is my first half with LS2 on B, okay? Then same thing goes over here. This time I'm going to take these 3 bits and they will become at the start, followed by 1, then another 1. So basically 1, 1, 0, 1, 1. 1, 1, 0, 1, 1. So after performing LS2 on both halves, when written together, this will be my sequence of 8 bits, right? And this will be known as C in this particular example, okay? After performing LS2. The next step is we perform P8, which is permutation 8, on C, which is this. And after that, the result will be my second key. So as we remember, this is P8. So first I need the 6th bit of B. Sorry, 6th bit of C. So first I need 1. Then I need the 3rd bit. We got 0. Then the 7th bit, we got 1. Then we got the 4th bit, 0, 0. Then we got the 8th bit, which is another 0. Then we got the 5th bit, which is 1. Then the 10th bit, which is 1. And finally the 9th bit, which is 1. Okay, so this is my final key 2. Okay, so first step takes place in which we have the initial 10-bit key. Notice that I'm not using the plain text here. Okay, we're not bothered about the plain text yet. We just want to first make both keys that we need. Okay, so these are my two keys that I'll be using in the further steps. So any questions so far?
No, sir.
Okay, now this is where it's going to get a little tricky. So we'll pay very close attention to what's going on over
Oh
here. Okay?
my god.
This is only the beginning. Yes, this is only the beginning. This is 2 steps. Okay, now step number 2. Okay, step number 2, we will be taking the 8-bit plain text, which is denoted by B, and apply IP. IP is what? Initial permutation, to get a variable with a sequence which will be called D. Okay, so again, bit position, since plain text is only 8 bits, I'm using bit position 1 to 8. This is my plain text. As we mentioned at the start of this problem, this was my plain, it's the same plain text, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, exact same thing. Now, initial permutation sequence goes something like this. First, I need bit number 2. This is bit number 2, 0. Then I need bit number 6. This is bit number 6, again 0. Then I need bit number 3, which is 1. Then I need bit number 1, which is 0. Then I need bit number 4, which is also 0. Bit number 8, also 0. Bit number 5, which is 1. And finally, bit number 7, which is 0. Okay, so this sequence will be my D. And how did I get D? I applied the initial permutation on my plain text. Done? Okay, so now I have 2 nibbles. From this one sequence, I have 2 nibbles. This will be my left nibble, bit position 1, 2, 3, 4. This will be my right nibble, position 1, 2, 3, 4. Left, right nibbles of what? Of D. We're gonna call the left nibble of D, D0, and the right nibble of D, D1, okay? So the green part mentioned here, that's the right nibble. The yellow part, or the orange part, is the left nibble, okay? 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, okay? Coincidentally, they're the same. Anyway, so now the next step is that we will calculate the sequence E. How do I get E? E is achieved by performing expansion permutation. E/P means expansion permutation on the right nibble of original D. So basically, I'm performing expansion permutation on the right nibble, this thing right here. Now, what is the expansion permutation? Expansion permutation means of the right nibble of whatever data you're talking about, I'm performing it on the right nibble. So I'm talking about the right nibble right now. I need the 4th bit first. So of the right nibble, D1, the 4th bit is 0. So write that there. Then I need bit number 1, which is also 0. Then I need bit number 2, which is also 0. And finally, I need bit number 3, which is 1. So the first part of expansion permutation, 4, 1, 2, 3 results in 0, 0, 0, 1. Second part states that this sequence is to be followed. 2, 3, 4, 1. So bit number 2 of the right nibble is 0. Then I need bit number 3, which is 1. Then bit number 4, which is 0. And bit number 1, which is also 0. So combining them together, I have a byte, 8 bits, which will now be known as E. Okay. And obviously E2 has also 2 nibbles. We got 0001 and 0100. Okay. Same rule here. This is bit position 1, 2, 3, 4. And this is bit position 1, 2, 3, 4. Okay. Any confusion so far?
No, not really, sir.
Okay. Now the next step is we're going to get F. How are we getting F? We're applying the XOR to E, which is this, with key 1, which we just calculated in the previous screen, right? I've written that over here as well. This is key 1 right here. okay? So I'm going to take this sequence and this E over here, and I'm going to perform an XOR operation, right? So this is going to be my result right here. This is my result right here, okay? So if you remember, XOR means different bits result in one, and same bits result in 0, right? So for E, I have 0 here, and key 1, I have 1 here. So 0, 1 should 1. So there's the 1 over here. Then E, I have 0 here, again 1 here. This should result in again 1, followed by another 0 here, then a 1 here. Again, I get a 1 over here. Then the fourth bit, I have 1 here and a 0 here, and again I get a 1 over here. Okay, let's start off over here. I have a 0 here, 1 here, 1, 1 here, 0 here, again 1, 0 here, 0 here, 0, 0 here, 1 here, again 1. Okay, so after the operation of E XOR key 1, I get this sequence of 8 bits, and we're going to call it F. Okay, now pay very close attention to what's happening to F. You see the different colors I've chosen for individual bits here, right? Let's just look at this first nibble. Let's look at this first nibble. For this first nibble, the red part is both 1, 1, and the blue part is 1, 1 again. I'm going to say that this red part for the first nibble is considered is the row number. Red part is denoting the row number, right? So row number 1, 1 for 2 bits, 1, 1 means 3, right? Similarly, so that basically means row number 3, and the blue parts means column number. So the red part is a row number. I think I said blue for this one as well, but red part is row number, and blue part is denoting the column number. So this red part represents row number 3, and this this blue part represents column number, again 1, 1, column number 3. Now row and column of what? Remember that we discussed these boxes in the beginning? This is S box 0, S box 1. So for the first nibble of F, I'll be using S box 1. The second nibble, I'll be using S box 1. For S box 0, I need to know what's happening inside row number 3 and column number 3. So row number 3, this is row number 3, this is column number 3, and what do I have value here? 2, right? This is 2 right here. So is this 2 in binary, 1, 0?
Sir, I have no idea what's going on.
Okay, I'll repeat it.
Why did you choose that as the column and that as the row?
That's the rule. The outermost bits are the row number, inner bits are column number. Same thing goes over here, row number, column number.
Yeah.
Okay? Okay, listen up. So this is row number 3, 1, 1, yani ki 3, and column
row 3,
number, column 3, right? This first nibble, it will be using S box 1. The second nibble will be using S box. The first nibble will be using S box 0. The second nibble will be using S box 1. Okay.
And we have these Xbox 0 and 1 tables beforehand, right?
Yes, and they are constant, predefined. They're not changing.
All right.
I showed you this on the first screen. We'll be using this. Okay. And there it is again. Okay. So initially for the first nibble, I get row 3, column 3. For S box 0, row 3, column 3 gives me a value 2. And as you can see here, I've written the value 2 in binary 1, 0. Okay. That's the first 2 bits right here. Okay. Now let's look at the second nibble. Second nibble, I'm dealing with row number 1, 1 and column number 1, 0. So this is row number 3, column number 2, 1, 0 is 2, okay? But I mentioned before, for the second nibble, I'll be using S box 1. So row 3, column 2 is the value 0. For 2 bits, I write 0, 0 to represent that. Now combining the operation of S box 0 and S box 1, I have this sequence of 4 bits only. representing the operation of S box, right? On the original 8 bits of F, okay? So when I perform S box on F, the resultant sequence should
Oh, you're
only,
writing the numbers in binary. All right.
I'm sorry?
You're writing the numbers in binary, right?
Always binary. Of course, data transfer is in binary, right? So resulting of first nibble S box is 1, 0. The second nibble is 0, 0. And I will be calling these 4 bits as G, okay? The contents of S box written in binary 2 and 0, okay? Now, after this step, since I have only 4 bits, I will perform permutation 4. That is 4 bits, not expansion permutation, but permutation 4, which actually just shifts around 4 bits, okay? So permutation 4 on G. So basically permutation 4 says that first I need the second bit. This is my second bit, 0. Then I need the fourth bit, which is also 0. Then I need the third bit, which is also 0. And finally, I need the first bit, which is 1. There you go, like so. So this combined is my permutation 4 sequence right here, 0, 0, 0, 1. Okay. After that, I have to calculate I. Okay, I. For calculating of I need what? I need H. I need D0. By the way, what was D0? D0 was the left nibble of D. This is my D0. I have to perform XOR between H and D0. So basically what happens is that I have D0, 0. First bit of D0 is 0 and H is 0. So 0 XOR 0, 0. And then I have D0 second bit also 0 and H is also 0, 0, 0, 0. D0 3 bit is 1 and we got 0 over here. So different bits, we get a 1 here. Same thing goes with D0 bit 4, 0, and final of H is also 1. So 0, 1, again, different bits, we also get a 1 over here. So 0, 0, 1, 1. So this is the sequence we're looking at for this part. And for I, the remaining part of I, you see it's written comma here. So basically what it means that the first 4 bits are going to be achieved by doing this. And the remaining 4 bits of I will simply be D1 written as it is. So I got D0 by performing XOR operation, followed by D1 written as it is. As you can see here, this is D1, 0, 0, 1, 0, 0, 0, 1, 0. So this is what my I is, right? XOR operation between D0 and H will get the first part of I, and the remaining part of I is D1 written as it is. Okay?
Got it, sir.
So this is my I. Finally, in this step, we achieve J. J is simply swapping the nibbles of I. So what that means is that I write this nibble first, 0, 0, 1, 0, and this nibble next, 0, 0, 1, 1 after this. So this is J. So far, so good?
So far, so good.
Okay. Now on the final stage of this whole process, okay? We got J. Remember this J? 0, 0, 1, 0, 0, 0, 1, 1. We'll be using that J over here. So 0, 0, 1, 0, 0, 0, 1, 1. So this is my J. These are the respective bit positions, 1, 2, 3, 4, 5, 6, 7, 8. We will perform expansion permutation on the right nibble of J to get K. So as before, when we did it for D, we're going to do it for J here. J0 is the left nibble. J1 is the right nibble. Right now, we're talking about the right nibble. So that means we're talking about 0, 0, 1, 1. So the right nibble, as before mentioned in green, the left nibble as mentioned in orange, just like before, right? So we're doing expansion permutation like we did before, but this time we're doing it on the right nibble of J. Expansion permutation was 4, 1, 2, 3, 2, 3, 4, 1. So again, this is 4, 1, 1 here. Then we got bit number 1, we got 0 here. Then we got bit number 2, which is again 0 here. Are you following this? From this bit right here. Then we got 3, which is bit number 1 from over here. So this is 4, 1, 2, 3. followed by 2, 3, 4, 1. 2, 0, 3, 1, 4, 1, and then 1, 0. So expansion permutation performed on J1 results in 1, 0, 0, 1, 0, 1, 1, 0, which we are going to call it K. Okay. Next, we got to perform L. We got to get L. Now, how are we going to get L? We're going to perform an XOR operation on K with key 2. Okay, remember that we calculated another key in the first step. Now we're going to be using key 2 right here. This is my key 2 as we calculated before. This is
One sector, expansive permutation, we do it on right nibble first, then left nibble?
No, just the right nibble. We're not doing it on the left, just the right nibble.
And then what about the last 4 digits of K?
That's is again the same right nibble.
Oh, okay.
The sequence changed. You see,
Only on
2, 3, 2. Pay attention. Bit number 2 comes first. This 0. Then bit number 3 comes first. Then next, this is 1. Then we got 4. This is 1. And then finally we got bit number 1, which is 0. So we're arranging only the right nibble. First 4 bits are using the sequence 4, 1, 2, 3. Bit number 4, then 1, then 2, then 3. Now the remaining 4 bits are following the sequence bit number 2, then 3, then 4, then 1. All on the right nibble. It's the exact same thing as before. So basically what expansion permutation does is that it takes one nibble and creates a whole byte out of it. Okay?
got it.
Okay. So after that, when we got E, we got key 2. Now we got to perform an XOR operation with E and key 2. So this is, E and K. K and key 2. This is K right here. So the first bit of K we got 1 and key 2 we got 1. So the result is 0. Secondly, we got 0 for K and key 2 we got again 0. Result is 0. Are you following this?
Yeah.
Then the next bit we got 0 and third bit of key 2 is 1, resulting in 1. Then we got 1 and then we got 0 on key 2, resulting in 1. Then we got 0 and key 2 is also 0, resulting in 0. And we got 1 and then key 2 it also has 1. Then we also got a 0. Then 1, again 1, it's also 0. Final bit of K is 0. And for key 2 is 1, resulting in 1. Okay. So we're going to call this sequence as L. Okay. Now we're going to perform S box on L like we did before, right? We got the left nibble of L. We got the right nibble of L. The outer bits of my left nibble will be the row number of SB1, SB0, and the inner bits will be column number of SB0. For the right nibble, the outer board bits will be the row number of the SB1, and the inner 2 bits will be the column number for SB1. So as you can see here, for the first nibble, I got row number 0 and 1, so that means row number 1. And column number, I've got column number 0 and 1, so that's also 1. So in that case, SB0, row 1, column 1 means 2. So that's 2 written here in binary. Okay. Now moving on to the right nibble, we'll be using SB1. SB1, we're looking at row number 01. So row number 01 is actually row number 1 and column number 00, which is column number 0. So in that case, for SB1, row 1, column 1 holds the value 2. So in that case, I have written the value 2 in binary. So 2 from SB0 and 2 for SB1. So both 2's written like so. So after performing S box on L, we get the result of this nibble 1010. And we're going to call this as M. Okay.
1 sec, sir. So left nibble is for SB0 and right nibble is for SB1.
Yes. It's written right here. It's written right here. Okay, it's written right here. Okay, so we got M, which is actually performing S box operation on L. This is M right here. Next step is we perform permutation 4 on M. So basically what that means is that I will be rewriting M using this sequence. So first I need bit number 2, that is 0. There you go. Then I need bit number 4, which is also 0. Then I need bit number 3, which is 1. Finally, I need bit number 1, which is also 1. So 0, 0, 1, 1. After performing P4 on N, I get this sequence of nibbles, and I will be calling that as N. We're on the final 2 stages, in which now what I do is I'll perform an XOR operation between this N and J0. This is J0. J0 was what? The left nibble of J. So this is my N, this is my J0, and let's see what happens when I take an XOR operation. 0, 0, 0. Agreed?
Agreed.
0, 0, again 0. Finally, 1, 1, 0, and then 0, 1. This is 1. Okay. I got this part, and the remaining parts is J1 written as it is. So J1, this is J1 right here. 0, 0, 1, 1. So when I combine these 2 nibbles together, I will get a byte, and I will be calling that as O. And when I have O, I just have one more step to do. That is known as the inverse permutation. Inverse permutation means rearranging the input byte to this sequence. In this case, I have the input byte of O, in which case it requires me to do what? Bit number 4 first. I got bit number 4 right here. Then I got bit number 1, 0. Then bit number 3, also 0. Then bit number 5, 0. Bit number 7, 1. Then bit number 2, 0. Bit number 8, 1. And finally bit number 6, 0. And this, my friend, is the final encrypted string generated from this plain text. This is symmetric encryption using the Sdes technique. This is my original plain text string, and when applied Sdes technique, I end up with this final encrypted string. Okay.
Got it, sir.